Hi, everyone. Hi. How's everyone doing this morning? Perfect. So welcome to, I think, the first not keynote session in this room, titled Base64 is not encryption, a better story for Kubernetes Secrets. My name is Seth. I work on the developer relations team at Google. This is my Twitter handle / GitHub handle / everything on the internet handle. If you have questions, concerns, comments, feel free to tweet at me during the talk, after the talk. Also, my direct messages are open on Twitter, so if you have questions that you don't feel comfortable asking in the public, feel free to shoot me a message. I'll also be around all day if you want to chat in person. So before we get started, I want to preface this talk by saying that there's a little bit of scare tactics in here. I'm going to show you some things that might make you feel insecure. That's not my intention, but I'm going to be kind of exposing some of the dirty secrets, no pun intended, in Kubernetes. But don't worry, we'll have some solutions at the end. So with that, let's go ahead and get started and answer a key question, which is, what is a secret? We often use this term interchangeably with personally identifiable information, passport numbers, credit card numbers, passwords, security, social security numbers. But what is a secret? And for the purposes of this talk, a secret is a credential, a configuration, an API key, or some piece of information that your application needs either at build time, compile time, or at runtime. There are other things which we may consider secret, like business processes or internal organizational charts, but we're not considering those for the purposes of this talk. We're mostly talking about machine secrets, like API keys or TLS certificates. So why do we even care? Why don't we just use Twitter or public GitHub repositories to store all of our secrets? Why do we have to keep these things a secret? Well, first, secrets are a very attractive target for attackers and hackers. Secrets often are easily leaked in public repos or storage buckets, or someone accidentally uploads their dot files to a public GitHub repo, and now you can impersonate them and act as them on different systems. And secrets often include overly broad permissions, particularly credential-based secrets. Especially if you work in a small company, it's very common that everyone has like root access or admin access to everything. You don't restrict, you don't practice principles of least privilege. So if an attacker is able to gain access to these credentials, they can do far more than the credential was ever intended. And there's 4 key ways in which you can protect secrets. The first is auditing. So this is on the other side. After you have implemented all of your security, you need to verify and log the use of every secret. The second is encryption. That's mostly what we're going to be talking about today, which is that you should always encrypt your secrets in transit using TLS, and at rest using whatever algorithm is approved for your organization. Third, you should rotate secrets regularly. API keys, certificates, especially things that humans don't have to remember, should have a relatively short lifetime. You should be rotating them weekly or monthly instead of having some API key that lives on for a year. That just increases your surface area for attack. It increases the chances of an attacker being able to crack that or having it leaked somewhere. And lastly, you should isolate where secrets are stored from where they're accessed. And that helps with the auditing and access configurations. So like I said, we're going to focus today mostly on the encrypt category. You should be encrypting secrets at rest and in transit. So what does that actually mean? Well, there's often multiple layers of encryption in a system. You may have something like machine-level encryption, which is where you actually encrypt the hard drive, something like Apple File Vault or Windows BitLocker, where you're actually encrypting the whole drive. And that whole drive is encrypted with one encryption key. And if an attacker is able to brute force that key or have access to that key, they have access to all of the data on the drive kind of in plain text. Similarly, kind of up the stack, you have file system level encryption. These are like encrypted volume mounts. Further up the stack, you have things like service level encryption. And then at the highest level of the stack, kind of what we have today is what we call application layer encryption. And this is where the application decides what data is encrypted with what keys. And generally, we recommend that you use at least 2 layers of encryption. So you might leverage something like application layer encryption or service level encryption, coupled with something like machine level encryption or file system encryption. And that gives you 2 layers of defense. So application layer encryption is the thing that I want to talk about today, because that's the one that's most relevant to Kubernetes. So application layer encryption delegates the cryptography to the application itself, meaning your application decides, does this piece of data get encrypted? With what algorithm does it get encrypted? With what key does it get encrypted? What cipher, what algorithm, et cetera. This is in contrast to something like full disk encryption, where the operating system is responsible and your application is unaware that the data is encrypted. It just reads and writes data. So application layer encryption is applied at the earliest possible step in the application lifecycle. Your application encrypts the data before it writes it to the database or sends it to another application or persists it to the file system. It also provides very granular encryption, right? Like I said, your application decides whether to encrypt or not encrypt this data. Your application decides with what algorithm and what key to encrypt or decrypt data. And lastly, application layer encryption protects data as it moves throughout the system. When you have something like file system level encryption, the moment that data is decrypted, if you give that decrypted data to a different system, you have exposed the plaintext data. With application layer encryption, you encrypt the data inside your application, and then you can give it to other applications and services, but you're not exposing the plaintext. You're giving them the ciphertext or the encrypted data. So it reduces the surface area for an attack, because application layer encryption basically keeps the data encrypted as it moves throughout the system. And this is especially important in microsystems architecture. And like I said before, you don't want to just use application layer encryption. You want to use application layer encryption coupled with something like full disk encryption or machine level encryption. OK, so now that we have this overview, let's talk about Kubernetes. And I have these 4 very sad faces here when we talk about the Kubernetes defaults with respect to secrets, because they're actually not very great. And I don't mean to hate on Kubernetes. This was not really in their initial design goals, and Kubernetes secrets are more of a transport mechanism as opposed to an actual secret storage. And what do I mean by that? Well, Kubernetes secrets are insecure by default. Secrets are stored in plain text in etcd. etcd is the backing store where all of Kubernetes stores all of its data, or most of its data. They're Base64 encoded, but they're not encrypted. And the reason they're Base64 encoded is so that you can support binary data, like certificates or arbitrary binary bits, but they're not encrypted. It's very easy to get the plaintext data out of a Kubernetes secret if an attacker has access to Kubernetes, the kubelet, etcd, or a backup of the file system on which etcd was running. The threat model is incredibly broad. Now, before we proceed, I want to make a note that if you're leveraging a cloud provider Kubernetes, something like Google Kubernetes Engine or EKS or AKS, those cloud providers have taken additional steps to protect you. So some of these things may not apply to you. But if you are running your own Kubernetes cluster on your own hardware, or you've bootstrapped your own Kubernetes cluster using something like kubeadmin or Minikube, you're most likely in the state which I'm about to describe. So let's walk through this visually. Throughout the rest of the slides, I'm going to use this little credit card icon to indicate a secret, but this could easily be a social security number, a passport number, some personally identifiable information, an API key, et cetera. In the default Kubernetes setup, we kind of have 3 components here. In the gray, there's the master VM. This is the node on which these containers are running. We have the Kubernetes API server, and then we have the etcd service itself. So a user or a service tries to save this secret to Kubernetes. Someone runs kubectl create secret. What happens? I have the secret, and I give that to the Kubernetes API server in plain text. It has to have the plain text. The Kubernetes API server then writes that data to etcd Base64 encoded. And again, encoding is not the same as encryption. This is 100% reversible. It's very easy for an attacker, which we will represent via this raccoon in all slides, to access that data. Now, it's important to note that this attacker can access this data in multiple ways. If an attacker has access to an online etcd server, for example, one that is publicly exposed to the internet, because that has never happened to any company. And if you don't believe me, you should check online websites that show you whether your etcd server is publicly exposed. They have access to this data. If an attacker has access to a file system backup of this VM, they have access to that plaintext data. If they have access to an encrypted backup, the moment that they brute force that encryption key for that encrypted backup, they have access to all of these plaintext secrets. Because on the file system and within the memory of etcd, within that container, all of these secrets are stored in plaintext. So I have a word for this. I like to call it encryption. Encryption is where you mistake encoding for encryption. And it's where you provide kind of a false sense of security because you call something secret and you make it hard to access, therefore people think it's secure. And like I said before, there's actually websites on the internet where you can go and find publicly exposed etcd servers. Now, etcd has other use cases beyond Kubernetes. It just happens to be the tool that Kubernetes uses as the backing store for most of its data. But you can find publicly accessible etcd servers, and you can find a lot of Kubernetes secrets using a query like this on Shodan. So instead of just kind of talking about this, I figured I would show you what this looks like. So I have set up a Kubernetes cluster using Minikube. And if you're not familiar with Minikube, it's just like a local tool. So it's running a Kubernetes cluster in a VM on my local laptop. So what I'm going to do here is I'm going to create a Kubernetes secret, create secret default. So all I'm doing is I'm running kubectl with a particular context because I have a couple Kubernetes clusters running. I'm creating a secret named demo, and I'm giving it a username of Seth Vargo and a password of secret. So let's go ahead and run this. And you can see that our secret was created. Now, this is a basic Kubernetes cluster. All I did was run minikube start. I didn't customize anything. I didn't change anything. I think it's running version 114 or 115 of the kubelet. Let's take a look at what is inside etcd. So I have this other script, which mostly exists because I am not good at typing, that runs kubectl exec. So that's just accessing the container. Again, there's multiple ways I could do this. And then I'm running this command right here, which is etcd-ctl get registry secrets default demo. This is the path in etcd. And what that's doing is that's asking etcd for the value that exists at that path. Now, if an attacker had access to the file system or this container, they would be able to run this command. If they had access to the file system, you could also get this data in other ways. But I'm going to go ahead and run this. Now, remember, this is a default Kubernetes setup, no customization, anything. And we get back this. So it looks a little garbled, but you'll notice that there's two key pieces of information in here. Here's that username that I set, and here's that password. Formatting is a bit weird because it comes back in kind of this half binary, half not binary format. But if you pipe this to hex dump, you can very easily get out both of these secrets. Right? So it's not very secure. Straight up, default Kubernetes setup, not very secure with respect to secrets. All of that data is stored in plain text, and it's very trivial for an attacker to gain access to those resources with a single command, as I showed here. So let's jump back into the slides and talk about some of the ways that we can kind of mitigate this. So one of the ways we can mitigate this is to leverage something called envelope encryption. So let me run through what envelope encryption is, and then we'll talk about how we can leverage it inside Kubernetes. So very simply, envelope encryption requires three pieces of information. Our secret data, which we already have because it's likely coming from the user. A data encryption key, which we'll see as a red key on all of the slides. Sometimes this is called a DEK, a D-E-K, a data encryption key. And then we need a key encryption key, or a KEK, which will be represented with green on these slides. Now, I'm going to show this to you, and it might be a little bit confusing, but it will make sense kind of as we walk through the animations in the slides. So we take these three pieces of data. So the user gives us their credit card number. The first thing we do is we generate a data encryption key specific for that credit card number. So we use the local system entropy. We generate a 256-bit key, and we encrypt that credit card number with that key. That gives us some encrypted bits or encrypted bytes. Next, we use our key encryption key, which may come from a management service like Google Cloud KMS or Amazon KMS, some managed encryption key. And we encrypt the key encryption key. We encrypt the data encryption key with the data that we just created. So now we have two pieces of encrypted data. We have the credit card, which is encrypted with our data encryption key. And then we have our data encryption key, which is encrypted with our key encryption key. It's turtles all the way down. We then concatenate those two pieces of data together, and we store them in our storage backend. So we put them in the file system, we put them in etcd, we put them on a tweet, it doesn't matter. So we have these two pieces of data. The first half of it is the encrypted credit card data. The second half of it is the encrypted key that encrypted that data. And we put it off, and we're good to go. So for an attacker, attackers need access to that green key in order to do anything. Because to reverse this process, we separate the data back out into its two parts. We then take our key encryption key, and we decrypt the data encryption key. We then have our plaintext data encryption key, which we can use to decrypt our credit card, giving us back, my animation went too far, giving us back our credit card. Now, how is this different than just encrypting the data right away? Why wouldn't I just use one key? Why would I use two keys and this envelope encryption? Well, there's a couple reasons. My clicker's being annoying. So the first reason is that every time you get a new piece of data, whether that's a credit card number or a passport number or an API key or a TLS certificate, you generate a new high entropy key for encrypting that data. So every piece of data is encrypted with its own unique key. And in fact, if you were to update the exact same credit card number, you would still generate a new key. That key exists for each piece of data. But then your key encryption key exists usually in a third-party system, like a key management service, that gets rotated on some fixed interval, like every 30 days or every 90 days, or in the event of a data breach. So what are the advantages of using envelope encryption over just the straight-up using a key? Well, by generating a unique data encryption key for each entry, you have a high entropy key. That means if an attacker is able to brute force the data encryption key that was used for password A, that same key is not used for password B. But at the same time, it allows us to crypto shred and revoke all of our data encryption keys by revoking the single key encryption key. Because if we revoke that parent key, it effectively becomes irreversible or unrecoverable by traditional means to get back all of that data. So by revoking one key, we revoke access to a bunch of different passwords or API keys or credentials that each have their own key. And it gives us a separation of concerns. We can easily version and rotate our key encryption keys separately from our data encryption keys. And this separation of concerns is really great for scalability. It also allows us to do the crypto shredding that I talked about earlier. So what does this have to do with Kubernetes? Well, Kubernetes 1.7 actually introduced this concept of envelope encryption into Kubernetes Secrets. So the way that envelope encryption works is that as a Kubernetes cluster administrator, you create this YAML file that I have here on the screen called encryption configuration. This is a YAML file. You can find examples of it on the Kubernetes docs. But you basically tell Kubernetes, I want you to encrypt secrets. I want you to use a provider for secrets. And you'll notice that I have two providers here. There's an AES CBC provider and a secret box provider. Kubernetes will use the first one to encrypt all of the data, but it can use the other ones to decrypt any existing data. And then within there, I have some keys. The keys are key value pairs with the name of the key and the secret. And that's a Base64 encoded 32 bytes of entropy key that I generated using OpenSSL. So this is a real configuration. You could put this in Kubernetes. And then you start your Kubernetes API server by passing in this additional encryption provider config, giving it the path to that file. And now Kubernetes will actually leverage those keys to encrypt your secrets. So let's take a look at what that looks like. So same diagram as before. We have our master VM, our Kubernetes API server, and our etcd, but we also have this red bar in the middle represented by our encryption configuration. So now, as a user, if I submit my credit card and it gets stored as a Kubernetes secret, the plaintext credit card will go to the Kubernetes API server. The Kubernetes API server that will then delegate to the encryption configuration which will use one of those keys to encrypt the data leveraging envelope encryption. So it will generate a data encryption key, encrypt the credit card, and then use the key that is in that YAML file to encrypt that data encryption key and store them side by side in etcd. So if an attacker has access to etcd, they no longer have plain text data. Yay, we're done. Or are we? If you're savvy about Kubernetes and you understand the Kubernetes setup, you might realize that if the attacker has access to the master VM, we actually haven't improved our threat model. Because if we recall to the earlier YAML file, our encryption keys were in plain text in that YAML file. So we haven't actually improved our security posture. So what are some of the drawbacks of this approach? Well, the first drawback, which I kind of glossed over, is that you have to generate the keys yourself. I said I generated them with OpenSSL. I can tell you the command, but you're going to have to run that. You're going to have to manually rotate the credentials. Every time you rotate those credentials, you actually have to restart the Kubernetes API server. So you have to schedule that work whenever there's no other jobs happening. There's no other, it's a downtime period, if you will, because you're going to restart the kubelet and the kube API server. Key management is ultimately your responsibility. You have to rotate those keys. You have to decide whenever to remove keys. You have to decide at what frequency. You have to generate the keys. It's a lot of work as a key manager, right? And that encryption configuration file can become tedious to work with over time. And you can't check it into source control because it includes your plaintext encryption keys or your plaintext CBC keys. So it just becomes very tedious to work with, and it's very difficult to recover if you make a mistake. Another drawback, which I like to bring up for the enterprise customers, or enterprise, people who work at enterprises and banks and fintech, is that there's no HSM integrations with this. So if you work in fintech or a regulated industry where you require hardware security modules, which are physical devices that manage crypto keys, there's no way to integrate with HSMs using this particular integration. And if you work in fintech, that's a pretty strong regulatory requirement for you. But quite honestly, the biggest drawback is that the underlying encryption keys are still stored in plain text on the file system. So if an attacker is able to gain access to that VM, you haven't improved your security posture at all. You've given an attacker an amazing laugh. They were like, ha ha ha, they tried so hard. But you haven't actually improved your security posture at all. And this was because Kubernetes 1.7 was kind of a stepping stone toward what came into Kubernetes 1.10. So Kubernetes 1.10 introduced this concept of a KMS provider, or an external secrets provider. And that looks like this. So that same encryption configuration, but instead of hard coding the actual encryption keys in the YAML file, we delegate encryption to some service listening on a Unix socket. So in this example, I'm just delegating to this fake thing that is listening on a socket file, but this can delegate to a number of different KMS providers. So what does this look like? Well, it's very similar to all of the other diagrams we've seen. We have our piece of credit card data. That credit card data goes to the Kubernetes API server. The Kubernetes API server delegates to the encryption configuration. But the encryption configuration doesn't actually do the encryption anymore. Instead, the encryption configuration delegates to this third-party KMS, something like Amazon KMS or Google Cloud KMS. The KMS provider manages all of the keys and the rotation schedules. It encrypts the data, or specifically the data encryption key, and gives it back to the encryption provider, which is then written to etcd. So it's very similar to before, except the keys themselves are managed by a third party cloud provider, or as we'll see in a little bit, any third-party service like maybe HashiCorp Vault. To get the data back, etcd goes back through, when the Kubernetes API server requests the secret, etcd goes back through the encryption provider config, delegates the encrypted data back to KMS, KMS decrypts the data, gives it back to the Kubernetes API server, which gives us back our plaintext data. So even if an attacker has access to the master VM, particularly in an offline attack where they have access to a backup of the master VM, they don't actually have access to KMS. And there's a few reasons for that. First of all, we can leverage file system permissions to obfuscate or prevent access to that Unix socket. But we also manage the permissions between the encryption provider configuration and the third-party KMS out of band. So we can refuse to allow access to a master node to access the KMS provider by leveraging some built-in cloud identity. For example, if this VM was not signed or is not running in a particular project or a particular region or a particular ARN, we can prevent it to have access to the KMS provider. So even if an attacker has access to the backup, they can't use that backup to communicate with the KMS provider. So in this world, we've actually dramatically improved our security posture. If an attacker has direct access to etcd, they have encrypted bytes. If an attacker has direct access to our master VM through SSH or something, we haven't really improved our security posture because they can call the KMS provider directly. But we have auditing and logging on the other side to detect those anomalies, and we can cut off access without revoking the keys, because we can just revoke the permission. If an attacker has direct access to a backup of our master VM, we can restrict access because we can prevent that VM from accessing our KMS keys, again, by restricting access by project or by ARN or other restrictions based on your cloud provider. So we've pretty dramatically improved our security posturing, but how hard is this to actually do? Well, it turns out that, why is my clicker being weird? It turns out that the community has already done a lot of investment to try to make this easy for you if you're running and operating your own Kubernetes cluster. So there is a couple different open source tools that kind of, as their names imply, manage these third-party KMS providers. We have the Google Cloud Platform Kubernetes Cloud KMS plugin. So this delegates access to Google Cloud KMS. The Azure/Kubernetes KMS plugin delegates the key management to Azure Key Management Service. The AWS encryption provider delegates access to Amazon Key Management Service. And then Oracle actually has a Kubernetes Vault KMS plugin, which delegates KMS management to HashiCorp Vault's transit backend. Shameless plug, because I work for Google, we actually have a way that you can set this up on GKE yourself. So if you want to use your own keys to manage data that's encrypted in GKE, you just specify the encryption key when you create your cluster, and we will use that key to encrypt all of your data. On GKE, your data is always encrypted. We always encrypt the data at rest, and we always encrypt it with a key. But with this integration, you actually have control over that key. So you can give us the key ring that you want us to encrypt your data with, and you can revoke it at any time. So this does introduce a question, which is like, how do I authorize Kubernetes or the master VM to be able to talk to my key management provider? Right? If I hard code my AWS access keys or my service account credential on that VM, if an attacker gets access to that VM, they can just impersonate me. So how do I prevent that? Well, the answer on a cloud provider is very simple. It's IAM. You can leverage identity and access management on the VM to trust the instance as a user. For example, on AWS, you can use assume role. So you can actually have the instance itself assume a role that gives it access to talk to the KMS provider. If an attacker has access to a backup of the VM, that VM won't be able to assume role because it doesn't meet the requirements. It's not in the right account. It's not in the right region. On Google Cloud, for example, we actually have internal mechanisms for how we trust or distrust a VM. You delegate that privileged access management to the cloud provider, though. So you basically have to trust that the cloud provider is doing the right thing here, and you probably already do that because you're probably already leveraging IAM for managing resources in the cloud. And then lastly, one way that you can harden this even more is you can separate concerns. So your etcd nodes, the containers or the physical VMs that are running etcd, don't need access to KMS because the Kubernetes API server is the thing that makes those API calls. So you can actually generate unique permissions, unique access keys, unique identities for these different nodes in the system. And don't give etcd nodes the ability to talk to KMS. They don't need it. That way, if an attacker does compromise that node, they have no way of communicating with KMS, even if they're on that node in real time. They don't have access to talk to KMS. They just have access to the encrypted bits. So separation of concerns is always a really great pattern for anything security related. So this brings up my last hypothetical question, which is, what if I'm not on a cloud provider, I'm running on-premise, I have my own data center, I have my own hardware, how do I do this? I don't want to manage all of those keys. And this is where something like HashiCorp Vault can come in. So very similar to what we saw in the KMS provider, HashiCorp Vault just is the KMS provider, but you can run that on-premise. Now, you could also talk to a cloud-provided KMS from on-prem, but let's assume your threat model doesn't allow you to use the cloud. You could run a local HashiCorp Vault cluster and leverage Vault's transit backend. Just like with KMS, the plaintext credit card will come into the Kubernetes API server. The API server will then delegate to HashiCorp Vault. Specifically, it uses the transit backend, which is like key management as a service. Vault will encrypt that data, give back the encrypted data, which then gets stored in etcd. So let's take a look at what that looks like. So we'll jump back into the demo land. So I have a script again, because I suck at typing. Create secret vault. So this is the exact same command that I ran earlier, but with a different context. So I'm using the secrets-vault context, creating a secret named demo, username is Seth Vargo, password is secret. But what I've done in advance is I've actually configured this Minikube cluster to use application layer encryption with HashiCorp Vault. So I created an encryption config YAML, and I said, hey, here's where Vault lives. Fun fact, I hard-coded the IP address because it's a live demo. But I set the encryption configuration up, and now what will happen is when we create this secret, it'll actually take a little bit longer. It's about 300 milliseconds longer. I hope you all noticed. It's about 300 milliseconds longer than a standard create because we're doing that extra round trip going to Vault and eating the CPU time for the crypto operation, encrypted that data and wrote it to etcd. Now let me prove it to you. So running that same, so we'll access the Vault secret. So the same command I ran as before, again, just with a different context this time. We're going to run etcd cuddle get off of the demo secret. And what you'll see this time, hopefully, is this. Same secret, same everything, but we get back a bunch of gargly goop. And in fact, inside of this gargly goop, we can actually see that the Kubernetes encryption provider KMS plugin leveraged version 1 of the Vault plugin using the key named myKey, which is at version 1. And this is the, where is it? So this is the name of the key, and this is all of our encrypted data. And that's binary data. That's why my terminal is having such a difficult time showing it to you with lots of question marks and Unicode characters. This is what an attacker would have access to if they had direct access to etcd, if they had a backup of etcd, or if they had direct access to the master VM and were querying etcd. But the good news is that as an application developer, kubectl, as an application developer, I can just access the secret the same way. So if I were to ask for Kubernetes for the secret back, so kubectl, what is the actual command? Is it info? Someone help me out. Describe. Kubectl describe secret demo and my context. See, I told you I can't type. Secrets vault. Oh, I don't get back the plaintext. But you can see that the username and the password is like 9 bytes and 6 bytes. So every time I run this, and if I were to use the Kubernetes API server to actually access the secrets, like mounting them in a pod or mounting them inside a service or accessing them inside a service, I just get the plaintext back. So this is where, even though we're leveraging application layer encryption, your application doesn't actually know. So you can still use Kubernetes secrets as the transport mechanism. You're still leveraging Kubernetes secrets, whether you're using environment variables or volume mounts. They're still in plain text when they reach your application. When your application creates Kubernetes secrets, it all does so in plain text. But then Kubernetes is actually managing the encryption and decryption of that data for you and providing a relatively secure mechanism for doing so using application layer encryption. So let's jump back over to the slides. So to kind of wrap everything up, here's the summary slide. If you take away one thing, it's this slide. Use at least 2 layers of encryption. So application layer encryption is a really good top-level encryption. File system or machine-level encryption is a really good low-level encryption. This protects data as it moves throughout the system and as it's stored on tape backups. Rotate keys regularly. Make sure you rotate not just your data encryption keys. You should be creating a new one each time you write data, but also rotate your key encryption keys on some regular schedule. I generally say that anything more than 30 days is too long. You should be rotating your key encryption keys at least every 30 days. Some organizations rotate their keys every 6 or 7 hours, right? The more frequently you rotate those keys, the less likely it's going to be for an attacker to gain access to them and brute force them. And then you can clean up your old keys later after you decide that they're no longer necessary. Leverage envelope encryption. Envelope encryption has a lot of advantages, particularly with scalability as it relates to encryption and security. It gives you a single source of key encryption keys, particularly if you leverage like a KMS provider. You can revoke one of those keys and crypto shred all of the data. But each piece of data is encrypted with its own key so that an attacker can't brute force and then kind of O-event operation decrypt all of your data. So you're using unique keys that are all tied up to a central key management system that allows you to quickly revoke access kind of in the event of an emergency. It's also incredibly scalable. It scales to as many things as you need because you have n data encryption keys, and those data encryption keys can be represented by like a significantly smaller portion of key encryption keys. And lastly, and most importantly, if you are running your own Kubernetes cluster, if you're on bare metal or maybe you're on the cloud but you're choosing not to leverage a cloud provider KMS, you're just running on VMs and managing it yourself, please leverage an external KMS provider. If you're on a cloud, use that cloud's KMS provider. Like I said, there's open source plugins. They're pretty easy to set up. If you're not on a cloud and you can't use the cloud, leverage something like HashiCorp Vault's transit backend. That will protect your Kubernetes secrets from prying eyes, rogue employees, and potentially save you from being on the front page of Hacker News. So please do that unless you want to be on the front page of Hacker News, and then don't. So that's all I have for you today. Like I said before, my Twitter handle is up there. If you have questions, comments, complaints, concerns, feel free to tweet at me, and my direct messages are open. We have about, 10 minutes for questions. So I'm happy to take any questions y'all might have. In the middle. I can't hear you. Great. So the question is, if you rotate the key encryption key, does Kubernetes automatically, or specifically, does the Kubernetes plugin automatically re-encrypt the old data, or the old secrets, the existing secrets? The answer is no, and that's OK, because when you rotate a key encryption key, you don't disable the old one. So all of the old secrets will be decrypted using the old key. New secrets that are created will be created and encrypted with the newest key encryption key. There's actually a little script on the Kubernetes website that runs like kubectl get pipe kubectl replace that will basically download every Kubernetes secret and re-upload it, and that would force all of the secrets to use the latest key encryption key. But in practice, it's actually probably better from a security modeling perspective to rotate the key regularly, and then newer secrets will use the newer keys, and older secrets are encrypted with the older keys. And then whenever you're about to do an audit or a compliance check, you can go through and do the kubectl replace of all of the secrets and then delete or destroy the old key encryption keys. But no, it's not automatic. It's just new things will use the new version and old things will use the existing old keys. Good question. Other questions? Right next to him.
This approach makes sure that Kubernetes doesn't store things in plain text, but it is still passed to the container in plain text, either via environment variables or API calls. What can we do to solve that, or is that necessary in normal use cases?
So I think the question is, this solves the storage problem, but it doesn't solve the runtime problem. Secrets are still available in environment variables, and how do I prevent my application from accidentally leaking those credentials, basically. So this doesn't solve that problem because your container is actually unaware that any of this is happening. Right? Your container still gets the plain text secret. If you want an even further down the stack integration, you can push application layer encryption into your container or into your application. This tightly couples your application to a KMS provider, though. So you would actually write code, Go code, Ruby code, Python code, in your application that called the third-party KMS provider from within your app. That tightly couples your app to the KMS provider. It makes local development kind of annoying, but that gives you that additional level of security. We actually have an open source tool on GCP called Burglass that integrates with Kubernetes that does a little bit of this for you. It injects a sidecar container, which is another option. So your application still sees the plain text environment variables. But the end answer is that you need to secure your application. You need to make sure that your app is not like dumping its environment whenever it crashes. You need to make sure that no other processes are running in that application because they are plain text at that point. Other questions? Yeah.
So in your experience, what would you say, is the most common use case in terms of efficiency and security? I mean, what people use the envelope secret management with Kubernetes, or do they do some kind of custom bootstrapping of their applications and integrate directly with KMS?
Yeah, so the question is, what should I do? It really depends on your threat model, and this is something I've been talking a lot about this year is like developers need to understand the threat model for their application or their service. You should spend 20 minutes or an hour writing up a document that explains the threat model. Like, these are the things we care about, these are the things we don't care about, these are the assumptions we make. Like, we inherently trust our operating system. We inherently trust our CPU. I don't know if any of you saw, there's like 2 major CPU vulnerabilities yesterday. Like, making those assumptions and writing those down will then dictate what type of encryption that you're going to use. If you decide that you're going to trust Kubernetes Secrets, then you should use the Kubernetes encryption providers. If you decide that you're not going to trust Kubernetes Secrets, you should build directly into the application. But you need to build a threat model and document a threat model for your application first. And that way, whenever some other team comes to you and says, what's your threat model, you can just give them this document. And it starts kind of a shared conversation. One more question. Yeah? How do you make sure that the intruder can't go to your KMS? So this is a good question. By default, identity and access management on cloud providers is deny. So you actually would have to explicitly give an attacker access to KMS or do something really stupid, like open it up to all users. It's also worth noting that KMS is a service that has like a bunch of different operations, and generally IAM is by operation. So you have an encrypt permission, you have a decrypt permission, you have a create key permission. So in general, you'd use principle of least privilege to generate just the required identity and access management permissions needed, and you would assign that directly to the Kubernetes VM and never give that out to an attacker, for example. Now, if an attacker is able to gain SSH access to a running VM inside your project or your resource, then they would be able to impersonate that account because they're on that VM. At that point, you have larger problems, probably, because you have the ability for an attacker to directly SSH into your network. So like, there's other things that are part of the threat model, like making sure that people can't SSH into VMs, making sure that you have like bastion hosts so that things aren't publicly accessible on the internet. But everything's denied by default, so unless you actually give access to an attacker, they shouldn't have access. I think that's all the time we have, but I will be around for questions, comments, complaints, and concerns after this and also the rest of the conference. So enjoy the rest of the event.